everyone. My name is Saeed Maliki and I work at Microsoft Research. I just wanted to say that every year we find talented students from all around the world and we get to work with them on cool projects. This work was jointly done by Zixin Kai and Xinyang Liu during their internship at MSR, which will be presented in a moment by Xinyang. If you would like to work on similar projects, please reach out to me using the email address shown on the slide. With that, I will let Xinyang present this work.
My name is Zhengyang Liu. I'm going to talk about our work on synthesizing optimal communication collectives. This is a joint work with my friends Zixian, Said, Madang, Toad, Jacob, and Ollie. I will start my talk with some backgrounds. Today, semiconductor companies such as NVIDIA and AMD are building deep learning servers that are specialized for training large-scale machine learning models. These machine learning servers usually contains multiple GPUs in one node, and new high-performance interconnects are introduced to achieve high data movement performance. Usually, the topology of those systems are designed with the consideration of physical constraints, such as signal integrity, cooling, and the physical layout of PCBs. Different systems have different topologies. Communication between GPUs is on the critical path of data parallels in deep neural network training. For portability, a set of communication routines or collectives are widely used to abstract the common communication patterns. For example, altogether shown in the left-hand side, each node sends its own data to all the other nodes in the system, and the red diagram shows the all reduce. The collective reduces the value across all the nodes in the system and then distributes the results to each node. NVIDIA and AMD implemented these collectives, optimized them, and shipped them as libraries. The NVIDIA's library is called Nico, and the AMD one is called Rico. Those two libraries are heavily used in nowadays neural network training. However, different topologies require different communication algorithms to maximize the performance. In other words, one algorithm that works well for topology A may not work well for topology B. And these state-of-art libraries only provide general approaches, such as the ring algorithm and the tree algorithm. Today, these communication algorithms are written and optimized manually. The issue is that manually optimizing these algorithms require a huge amount of human effort. And more importantly, the optimality of these libraries are not guaranteed. So to solve above issues, we created the Synthesized Collective Communication Library. We pronounce it as SCCL. SCCL detects the hardware topology, synthesizes the algorithm using this way, and finally generates CUDA code that implements the synthesized algorithm efficiently. Let's take a look at one of the deep learning servers we studied in the paper, the NVIDIA's DGX-1. DGX-1 has 8 V100 GPUs, and the topology is shown on the right-hand side. Each vertex is a GPU. The GPUs are connected with NVLinks. Each edge in each direction has a bandwidth of 25 gigabit per second. Certain pairs of GPUs are connected with two edges. So what is an optimal collective algorithm in this topology? To answer the question, let's go through some of the basic setups for the algorithms. Each GPU starts with an input buffer. We split the input buffer into a number of chunks. The algorithm proceeds in global steps. A system-wide synchronization is performed between each step. And in each step, each GPU sends at most one chunk on one link. GPUs with double links can transfer at most two chunks in one step. Here, consider the altogether problem. All GPUs send the input buffer to all other GPUs. SCCL is able to answer, it is possible to have it done in 4 chunks and 5 steps. And how about 1 chunk and 1 step? Here, each question is a subproblem, and a satisfiable solution corresponds to an algorithm. In this work, we used the alpha-beta model for estimating the latency of SQL algorithms. That is, for a single link, sending a buffer of L bytes takes alpha plus L beta time. Here, alpha is the startup cost. For instance, the overhead of initiating a transfer can be counted towards alpha, and beta is the inverse bandwidth, or the time spent for transferring a single byte. This plot shows the latency when sending buffers of different sizes on NVLink. Clearly, we can see that alpha-beta model is able to estimate the latency with respect to the buffer size. When the size is small, alpha matters and the curve is flat, and as the input size increases, the latency grows linearly. If an input buffer of size L is split into C chunks, the size of a chunk is L over C, and transferring one chunk costs L over C times beta. Therefore, under alpha-beta model, a SQL algorithm for an input of L with C chunk S step costs S alpha plus S times L over C beta. Let's have a look at how Algather is implemented in NVIDIA's NCCL library. In Algather, each node sends its own data to all the other nodes in the system. In NCCL, the Algather is implemented with a well-known algorithm called the ring algorithm. Basically, in ring algorithm, each node sends its data to the next node in the ring at the same time. In the following steps, each node stores the received data and sends it to the next node in the ring. A ring with 8 GPUs requires 7 steps to run the algorithm. And since DGX1 has 6 non-overlapping rings, the topology allows 6 instances of the ring algorithm executed in parallel. On each node, we split the data into 6 chunks, each ring algorithm transferring a chunk per step. Therefore, the overall cost of NCCL's ring implementation on DGX1 is 7 alpha plus 7 over 6 L beta. And is this algorithm optimal? The answer is the optimality depends on how much data we want to transfer. When we have a huge amount of data on each node to transfer, beta matters. Our cost model simplifies to 7 over 6 L beta. We proved its optimality in the paper. When the input size is large, 6 chunk 7 step is the fastest algorithm we can get on DGX1. We call the optimality where the input size is large, the bandwidth optimal. So what about the case where input size is small, or in other words, when we only need to transfer a small amount of data? The cost of ring algorithm here is 7 alpha. In this case, 7 alpha is not optimal, and our synthesizer has found a better algorithm. We call the optimality where input size is small, the latency optimal. What does the latency optimal algorithm look like for Algather on DGX1? Since the longest distance between any pair of GPUs is 2, it needs at least 2 steps for transferring a chunk between those pairs. So one-step algorithm does not exist. We ask SQL, and of course, SQL returns unset. So we make a reasonable guess. Is there a 2-step algorithm? The answer is yes. SQL successfully generated a 2-step algorithm, which was not previously known in any literature. This synthesized algorithm costs 2 alpha when the input size is small. The performance evaluation shows a huge speed up compared with NCCL's 7 alpha algorithm. As we have seen from the previous example, the optimality is a trade-off between latency cost and bandwidth cost. An algorithm may be bandwidth optimal, but it may not be latency optimal. Here, bandwidth optimal and latency optimal are only for the cases where input size is extremely large or extremely small. But what about other input sizes? Each non-zero and non-infinity input size should also have a corresponding optimal algorithm. All of those algorithms are algorithms on the Pareto frontier. And this kind of optimality are Pareto-optimal. Using SCCL, we have found all of the Pareto-optimal algorithms on BGX1. In the following slide, I will talk about how we build our synthesizer. Our synthesizer takes a bunch of arguments. C is the number of chunks, and S is the number of steps. Those two parameters decide the overall cost of the generated algorithm. When calling the synthesizer, we also need to tell what the topology looks like. In pre-processing phase, we tell the synthesizer where the data stays at the beginning of the algorithm as the precondition, and where the data stays at the end of the algorithm as the postcondition. Each data movement collective has its own specification for precondition and postcondition. By switching the precondition and postcondition, we can easily synthesize a different collective. With both precondition and postcondition, here we have our correctness constraint. If precondition holds, then the postcondition must also hold. Or in the other word, if the data is in position at the beginning, when the algorithm finishes, the data must stay at its destination. And we also have the bandwidth constraint. The number of transfers for a link must not exceed the topology's bandwidth limit. We send both correctness and bandwidth constraint to the SMT solver. If the solver returns set, then our algorithm is found. If the solver returns unset, then we can see there is no such algorithm exists. It is well known that some collectives are the inverse of other collectives. For instance, the reduced gather algorithm can be generated by inverting an algorithm for a gather, and a reduced algorithm can be generated by inverting an algorithm for broadcast. Most importantly, all gather can be done by a reduced gather followed by all gather. With this, all of the collectives can be synthesized by SCCL. SCCL has a code generator that lowers the synthesized algorithm to high-performance CUDA code. In the following slide, I will talk about our code generator. If the solver returns set, then we have a valid algorithm. We fetch the model from the solver. The model consists of a list of transactions. Each transaction records what chunk to be sent, where is the chunk's destination, and when the chunk is being sent. The code generator takes the list and lowers the transactions into CUDA code. When we implemented the code generator, we want to reduce the alpha or the startup latency and beta or the bandwidth cost as much as possible. For the lowering, we used the CUDA IPC open memory handle to create memory handles across different GPUs. Once the memory handles are created, we can start to move the data. The data may be transferred either by executing load or store instructions through a kernel or by using CUDA memcopy. In our measure, CUDA memcopy has a higher transfer bandwidth, leading to a lower beta cost, but the alpha cost is much worse than load or store through a kernel. Meanwhile, CUDA memcopy does not allow fused data movement and computation, so it requires extra steps for the collectives with computation, for example, or reduce. We implement both options, and the performance is discussed in the next section. Finally, let's talk about performance numbers. This figure shows all gather speed up over nickel for different input sizes. Each line represents an algorithm. We have 6 Pareto-optimal algorithms shown on the plot. To show the impact of using CUDA memcopy, we plot 2 versions of bandwidth optimal 6-chunk 7-step algorithm, a load store implementation and a CUDA memcopy implementation. The difference between the load store implementation and the CUDA memcopy implementation shows the significant impact the lowering can have on the performance. As we can see, SCCL is up to 2.2 times faster than Nickel's algorithm on small sizes and 1.1 times faster on large sizes. It is possible for SCCL to automatically switch between multiple algorithms based on the input size. In this case, SCCL will consistently outperform NCCL. This figure shows the all-reduced speedup over NCCL for different input sizes. Again, we plot one line per algorithm. For the input sizes that are smaller than 4 MB, SCCL is up to 1.8 times faster than NCCL. In middle sizes, NCCL is beating SCCL because our synthesized code has a high synchronization cost, so the performance suffers. Improving this would be a future work for us. And in large sizes, with the 48-chunk 14-step algorithm, SCCL beats NCCL by up to 1.1 times. All-to-all is a complex algorithm which is very difficult to write efficiently by hand. Unlike the collectives showed before, NCCL does not natively support all-to-all. Instead, NCCL suggests using 8 point-to-point exchanges, and thus the resulting algorithm is neither bandwidth nor latency optimal. This figure shows the all-to-all speedup over NCCL for different input sizes, and it demonstrates a speedup of over 6 times for large sizes and over 1.2 times for small sizes. This significant speedup really shows off the power of SCCL's automated approach to building algorithms for a specific topology. We also evaluated the Synthesizing All gather on an AMD-based Gigabyte Z52 system. The system has 8 AMD MI50 GPUs. The topology is shown on the right-hand side. The edges in the diagram are AMD HGMI links, and GPUs inside the boxes are connected by PCIe. The entire topology can be regarded as a ring. We used SCCL to synthesize 2 altogether algorithms, a 1-chunk 4-step algorithm and a 2-chunk 7-step algorithm. The figure shows the speedup over recall for different input sizes, and it demonstrates that the low latency 1-chunk 4-step algorithm is better at smaller input sizes, and high bandwidth 2-chunk 7-step algorithm is faster for large input sizes. In general, SCCL's generated code is faster than recall for large sizes, but slower for the medium and small sizes. Speaking of synthesis time, we measured the time required for synthesizing each collective. The longest synthesis task takes 2 minutes, and most of the tasks can be finished within 10 seconds. Now I will finish my talk with a conclusion. We introduced SCCL, a systematic method to synthesize Pareto-optimal collective algorithms. We studied a class of algorithms that captures a broad set of known algorithms and prove Pareto optimality of those algorithms. SCCL generates the implementation of those algorithms, and the implementation shows good speedup compared to manually tuned libraries in use today. This is all of my talk. Thanks for listening.